Hi and welcome back from the holidays. If that's when you're seeing this, that's the plan at least, is that we'll begin Module 3, Week 9, after the holidays on the 4th of October. Or I may have released it a bit early if people wanted to get fired up during the holidays. So yeah, we're moving on a little bit, and this is actually another one a bit like gas laws, which you might remember from the end of the last module, which is kind of off on its own. We're going to talk a little bit about wave motion. And again, I'm assuming that you've got some background knowledge already from junior secondary about waves carrying energy from place to place and so on. And that maybe you've done some calculations and so on, that you've done Snell's law, light, refraction, reflection and so on. So it's another little quick one that we're going to spend just a week on. And then we're diving off into electricity and all the fun that we can have with that over the next little while of this module. So wave motion, just very briefly, and some kind of revision and reminding. Waves carry energy from one place to another. So even ocean waves, actual waves that travel across the deep ocean, don't carry matter from place to place. If something's floating, it doesn't get carried forward by the wave. The water itself doesn't move from one side of the ocean to the other. What moves is the energy. So that up and down motion of the water is carrying energy. Now, when waves get into shallow water and break, then you'll see some water carried forward and the waves will wash up onto the beach a bit and so on. But at that point, you could argue about whether they're really waves at all, whether they're actually post-waves, they've broken, and the wave motion is not continuing anymore. There's no up and down, it's a forward motion. It's converted from one version to another. So waves generally do carry energy. Light travels from the sun to us, mostly high energy, ultraviolet and visible light travels from the sun to us, comes into our atmosphere. We use it for various things and it turns into lower energy infrared, which radiates back off into space. So that's where we get most of our energy from, as we talked about earlier when we were talking about energy. Waves in general, we divide them into transverse and longitudinal. Transverse means that the motion is at right angles to the motion of the wave. So in other words, if the wave is going left to right, the motion is at right angles to that. Or longitudinal waves, the motion is along the direction of motion. So if the wave is going left to right, the motion of the particles is vibration. And our most usual example of a longitudinal wave is sound. So sound waves, I'm speaking now in this room to this camera and its related microphones, and I'm compressing and rarefying the air between me and the microphone. The microphone then turns that into electrical waves, or electrical energy, I guess, that has a wave-like form, and we could put that on an oscilloscope and display what it looks like and so on. And we often use transverse waves to represent longitudinal waves, because longitudinal waves are really difficult to draw. You'll see my lovely, skilled, stylish drawing there. You'll see the compressions, the higher pressure points, where there are more particles close together, corresponding to the peaks of the transverse wave above, and the rarefactions, where the particles are further apart, corresponding to the troughs of the transverse wave above. That's what I tried to achieve, but it's really quite, it was relatively easy for me to draw that sine wave freehand and draw it on the board or whatever. It's not perfect, but it's good enough for government work. And as I say, the longitudinal wave is quite difficult to draw. So when we're doing things like analyzing the motion of sound in a woodwind instrument, whether it's an open or closed-ended tube, we won't draw a whole bunch of little lines to try and show a longitudinal wave. We'll map it with a transverse wave. In that case, actually the transverse wave is acting as a graph. Rather than a representation of the wave itself, we're graphing the pressure in the particular tube. But that's maybe a little bit further beyond where we need to get to. Knowing that distinction is helpful. Characteristics of waves, and again, this probably is revision, you're probably quite comfortable with all of this, but amplitude is how intense it is. I spend a fair bit of my time at heavy metal and extreme metal gigs. So the amplitude is the intensity of the sound, how tall the waves are, or in the case of sound waves, how compressed the compressions are and how rarefied the rarefactions are. So how powerful that is. And at a loud concert, you can actually feel the wind from the speakers moving your clothes as the intensity of that sound is hitting you. So the pressure, the height and the pressure, wavelength, we can measure it from, it's a little bit difficult to describe, but from peak to peak is probably easy, or from trough to trough, or from where it crosses the line going down to where it crosses the line going down again. So in other words, the same point on one wave and the next wave, the distance between those measured in meters is one wavelength of that wave. The amplitude is also a height, so in SI units it's measured in meters. Although that's true for transverse waves. For longitudinal waves it's a little more complex. It's because it's a pressure rather than a height. Frequency of a wave is how many peaks pass a point in a given time. So we talk about cycles per second, or hertz is the SI unit. So HERTZ, lowercase, as it always is for a person's name, and capital H, lowercase z. Hertz is the unit, and we often talk about kilohertz, thousands, megahertz, millions of hertz. Frequency is how many peaks pass a point in 1 second. Period is how long it takes one entire wave, one wavelength, to pass a point. And it's just the inverse. So f, we often use a lowercase f for frequency. We sometimes use a Greek letter nu, which is a bit like a kind of forward-facing v. But that's kind of confusing because we also use v for velocity. So I tend to use f for frequency. And we use lambda for wavelength. So the velocity of wave is how far a peak moves in a given time, so distance over time, like velocity always is, so that's pretty simple. People tend to call this the wave equation, but of course there's sort of Schrodinger's wave equation in quantum, which actually relates the distance and the velocity and uses second order differential equations and is way beyond where we want to be. So I'd be inclined not to call it the wave equation. Maybe it's a wave equation. Maybe it's a useful equation to use with waves. But V equals F lambda. Velocity equals frequency times wavelength. And that actually makes sense because the velocity is how many peaks pass a point in a given time. The frequency is how many peaks pass a point in a given time. And the wavelength is a distance. So if you think about the units, frequency is seconds to the -1. It's per second. Right? Period is seconds, and this is the inverse. So it's per second, seconds to the -1. And the wavelength is in meters. So meters times per seconds is meters per second, which is velocity. Right? That makes sense. For all of the electromagnetic waves, so radio waves, infrared, visible, ultraviolet, gamma rays, X-rays, that whole circus of various kinds of electromagnetic waves that we have. The velocity of those in free space is c, the velocity of light, 3 × 10⁸ meters per second. Right? Now, we know that with refraction, it slows down in certain materials that have a higher optical density, but it doesn't slow down by a vast amount. But so the velocity that you can use c equals f lambda if the wave you're talking about is an electromagnetic wave of any kind. If it's another wave, if it's a water wave, if it's a sound wave in a steel girder, or as well as a sound wave in air. If you haven't tried that experiment, it's quite fun. If you go to a very long steel rail, say the rail around a football ground or something, and bang on it with a stick or something, you will put your ear on it, or have someone else put their ear on it far away. They will hear the sound come through the steel faster than they'll hear it come through the air. So they'll actually hear 2 hits. One hit coming through the steel and one hit coming through the air for each one hit, because the velocity of sound in air is slower than it is in steel. If someone's hitting a railway line, like hammering a spike into a railroad track, the same kind of thing happens. So the velocity of the wave will vary depending on the material, but V equals F lambda will still hold. We know about reflection and refraction. Reflection is really easy. Angle of incidence equals angle of reflection. That's true for particles. If a ball bounces off something, in general, if there's not spin and a variety of complexities, but in general, angle of incidence equals angle of reflection. A laser or a water wave hitting a beach again, in general, if there aren't issues with the depth of the water and other things that bend it, but in general, if a water wave hits a beach or a wall, actually is even better, it will be angle of incidence equals angle of reflection. Refraction, we know that when light moves from one medium into another, so a laser goes from air into water and out again, a laser goes into a diamond, a beam of white light goes into a prism, light will be slowed and bent as it changes into a more optically dense medium and speeded up and straightened, made closer to the direction of the normal when it goes from a more into a less optically dense medium. Why am I insisting on optically dense? Because we often say a more dense or a less dense medium, but that kind of connotes mass dense, number of kilograms per cubic meter or whatever, right? But optical density is not necessarily the same. So diamond is one of the most optically dense materials. It has one of the highest refractive indices, but it's not more physically dense, more mass dense than other materials. So being specific, saying optically dense is probably helpful just in being clear about what we're actually saying. We don't mean mass dense, although water is more mass dense as well as more optically dense than water, than air, sorry. So the two things are independent of each other. We can get constructive or destructive interference. We kind of know that. Or in between, like it's not only one or the other. It's not that waves are either purely constructive, building on one another, or purely destructive, cancelling one another, so that you get zero displacement. Obviously, they go through all of the possible relationships and phases, right? This is going to be a lot easier to explain in the example video when I'm drawing little diagrams and little waves and so on. So have a little patience on it for that one. But basically, if there are whole numbers of wavelengths for each of them, or if their difference, sorry, in distance differs by a whole number of wavelengths, so if it's 0 or 1 or 2 or 3, then they'll interfere constructively. If it differs by half wavelengths, a half, 1, 2, etc., half, 1 and a half, 2 and a half, it will destructively interfere. And this is how we get that diffraction grating effect, that the light and dark bands from a double slit experiment and so on. So we'll talk a bit more about that as well. But interference in general, adding some legs to that, distance apart times the sine of the angle. If it's a whole number, n, so n can equal 0, 1, 2, 3, 4, 5, 6, 7, or if it's a half number, you'll get destructive. Constructive whole numbers, destructive n minus a half is always going to be a half number, because n in this case is 0, 1, 2, 3, 4, or 1, 2, 3, 4 if you prefer. So as I say, again, this is probably a lot easier to do as an example calculation drawing type video than in this kind of video.